Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we are very pleased to have Moshe Tenenholtz here from the Technion, and I guess he's in the second week of his 2-week visit. He's working with a lot of us on something different from what he's going to be talking about, which is mediators.
Thank you, Jennifer. So the topic of this talk is called mediators. Basically, the idea is to basically expose you to this line of research that is very ambitious one, basically. That this talk is basically on the foundations of game theory. So I don't know what is the exact background of everyone here, but I'll try to that at least the basic concepts will be completely clear. So in many cases there will be like equations written and I'll speak about them in English. So I hope that it will convey the thing. So really this is my ambitious goal for this talk. This is basically, this is like an overview or introduction talk to the more recent work on mediators, which basically joint work with Itai Ashlagi, Dov Monderer, and Ola Rozenfeld. Basically, this particular approach that I discuss here started from a paper titled Program Equilibrium, and it can be viewed as an extension of it. In fact, this work has inspired some work also by others. Ehud Kalai and Adam Kalai had some work on this, Dov Summit and Ehud Lehrer also. And this brought us to this topic of mediators that we'll describe in a minute. So to just jump into the water, I'll start with a very major challenge to game theory, or multi-agent systems if you wish. So we all know that it's the idea that of providing an agent with some strategy profile or some behavior that will be stable against deviation. So if you talk about unilateral deviation, this is basically the Nash equilibrium. So one question is whether giving this suggestion to the agents will suffice. And the answer is, of course, not. Because there may be more sophisticated kind of deviations. In particular, what bothers people for many years is the idea that providing agents with strategy profiles that are stable against deviation by subset of the agents is a desired property, or in game theoretic terms, the terminology is that the existence of strong equilibrium is the most desired property. Unfortunately, such situations rarely exist. So to make it concrete, let's look at the following classical example. It's just a prisoner's dilemma. You cannot have a talk this related to really game theory without a prisoner's dilemma. So you have here the prisoner's dilemma that you all know, and you can cooperate or defect. And there is only one equilibrium here, basically a dominant strategy equilibrium, that tells both agents to defect. So this is the only, in a sense, rational behavior in this context. However, if both agents deviate from defection to cooperation, then both of them will gain. This will mean, in the terminology of game theory, that mutual cooperation is not a strong equilibrium, because both agents can deviate and gain. More generally, in larger games, strong equilibrium requires stability against deviations by subset of the agents. So what is a mediator? We'd like to use mediators in order to enable us to obtain such kind of behaviors. So what is the agenda? I'll jump to the end. The agenda is we don't like to compromise on solutions. We basically think that in many systems there is a notion, a reliable entity, which we call a mediator. And the idea of this mediator it will be to try to lead the agent to obtain this desired behavior. So example will be a broker, a bidding club. We have examples in auctions that are towards the end. Someone that likes to collude in an ad auction, help you to collude there, or whatever. So this will be, all of this, roughly speaking, a mediator. So the classical example in the literature is a mediator that can flip coins and recommend behavior to a set of agents in a way which improves the social surplus. So this mediator is called in the literature correlated equilibrium, communication equilibrium. But we are after a more general type of mediators. So in our work, a mediator is an entity that can play in the given game on behalf of agents that give it the right of play. So agents may decide to participate in the game directly. But this mediator can offer them a contract. He is reliable. And they need to decide whether to give him the right of play or not. So the best thing is to just use an example. Here is an example of a contract that a mediator can offer in the context of, let's say, the prisoner's dilemma. The mediator will say, if both of you give me the right of play, or select to use the mediator services, then I'll perform cooperate on behalf of both of you. If only one of you select to use my services, then I'll perform defect on behalf of this guy. So the agents now, or the participants, need to decide whether to accept this conditional contract or not. So what happens here? The agents are not forced to use the mediator services. They can go and participate in the game directly, or to say, I'll use this contract. So basically what happens, this translates this game into a new game. In this game, you have the original actions, but you also have new action of approaching the mediator. And believe me that I've put here the right numbers. It's just what happens by this contract. So in this game, it turns out to be that it has a nice property. It has a strong equilibrium. An equilibrium is stable against deviations by coalition. And this equilibrium will be the approach to the mediator. So what will happen here, both agents will use the mediator services, which will lead them to a pair of 4 each. So we get cooperation, basically, using this mediator as a strong equilibrium in the mediated game. So we call strong equilibrium in a mediated game a strong mediated equilibrium. So we get cooperation in the prisoner's dilemma as the outcome of a strong mediated equilibrium. This is what we get here. This is just a simple example. So the question is, how far this can go? How much mediators can help us? And there are many things here to do. In fact, I need to define things a bit more formally. I'll go very briefly over some formal definitions. So bear with me, and just, I hope that you'll get at least the idea of this definition. So how is strong equilibrium defined by Aumann already in 1959? And we'll refer a lot to this paper, which is a very seminal paper. Says the following thing. You have a bunch of agents. Each agent has a set of actions or strategy. And each agent has a utility function, but maybe this tells what will be the reward for any action profiles. So an action profile will be called a strong equilibrium of type 1. We'll call it type 1. This is what has been defined by Aumann. If for every subset of the players and every strategy profile of them, there exists at least one agent that will not benefit by this deviation. This is the definition by Aumann. Now, this can be extended to strong equilibrium of type 2 when we talk about mixed strategies. So roughly speaking, it's defined here. If we talk about mixed strategies and you don't like that agents will gain in expectation, then this is called strong equilibrium of type 2. And to make a long story short, strong equilibrium of type 3 that we'll be interested in this talk is a very, very demanding concept. Rarely discussed in the literature because in the only cases that already strong equilibrium exists, this thing doesn't exist. It talks about the following thing. We'd like to be stable against correlated deviations. So 3 of us may gather, flip coins about what will be the strategy, and in this way, we will be able to gain. All of us will be able to gain. So if you are stable against correlated deviations like that, you have correlated strong equilibrium or strong equilibrium of type 3. So to make, again, those of you that don't know the literature, basically, this is really nice solution concept. The only problem that it doesn't exist. It's very, very hard to find situation where it exists. And we don't like to compromise on this. So we'd like to use mediators. A lot of symbols, but the idea is as follows. So what is a mediator? And this will be later extended. Basically, you have a set of messages that you can send by each agent. So these are the things that that each agent can tell the mediator when it likes to give you the right of play. And there is a conditional contract for any subset. which means a mediator determines a correlated strategy for the players who give it the right of play as a function of the messages received from them. Is it clear? So it's just a conditional contract which specifies here is very generally. And what happens is if you take this mediator and the original game, this defines a new game, gamma m. What the agents can do in this mediated game, they can either use the original actions or submit messages to the mediator. Formally, we need to require that these sets are disjoint, but let's forget it for this setting. And the utility function of each agent in the mediated game is written here, but what is important, it's what is naturally implied by the conditional contract and the actions of the agents that didn't give the mediator the right of play. So what is important, it is written here, is every strategy, correlated strategy in the original, in the mediated game, defines at end some behavior in the original game, and therefore everything is well defined. This is all I like to say. So you have a game, given game, you introduce this mediator, this creates a mediated game, and in this mediated game you can analyze it and say there is an equilibrium, and we call it a mediated equilibrium. So formally, what is a strong mediated equilibrium? It's given a strategic form game, a correlated strategy is a strong mediated equilibrium if there exists a mediator and a vector of messages such that if we submit this message to the mediator, this is what we tell the mediator, what will be implemented is exactly this correlated strategy. Moreover, doing that is a strong equilibrium of type 3 in gamma m. So what is written here, again, let's read it. I hope that I don't lose you. You are quiet today. So the idea of strong mediated equilibrium is that the desired output will be implemented as a strong equilibrium of the mediated game. And recall again that the agents are still free to participate in the game without the use of the mediator. So basically, we'd like that these good things will happen by using the mediator. So we'd like to implement some behavior using the mediator. So now I need to do like 3 things. And I think that in this talk, I'll emphasize one. And the 3 things that we are doing are, first of all, connecting it with the foundations. It turns out that we need to go to 59 in order to see how this connects to game theory. Then we need to say a few things about the structure of mediators, and things like that. And the third thing, which is perhaps the most interesting one to people that are not that familiar with the foundations of game theory, is how much mediators can help. So let's say just a few words. So I'll go over several slides quite quickly, but please stop me if the message is unclear. So first of all, when one starts with the whole setting, one can talk about more general setting. So what is a more general setting? There can be many mediators. Many mediators, and you can approach a particular mediator and do various kind of crazy things. And so the setting may look much more elaborated. The basic proposition that we have here is the existence of many mediators that the agents can approach does not help beyond the use of a single mediator. So if you like to implement a particular kind of behavior, the fact you have many mediators in the systems will not help you. Again, I'm going it very fast, I know.
But if the mediator gains something from this behavior, then other mediators...
In fact, even this is not completely correct. In order to make it, we need to introduce monetary transfers into this, how the mediator makes money. In terms of, but in this talk, for this particular thing, we don't assume that the mediators are just, volunteers. They like to, but of course, we have answers also for that kind of thing. So the other thing that one can think is, what about the use of a new mediator in the mediated game? So someone can come and try to mediate behaviors when you already have a mediator. So it turns out that this kind of new mediator in already mediated game cannot help. What I'd like to mention is the notion of minimal mediator, which will make your life easier, and hopefully you follow that. So a mediator will call minimal if each message space is just a singleton. In such a mediator, each agent either just gives the right of play or not. So, yeah, Kamal.
How do you know a game is already mediated?
What do you mean?
You said that a new mediator will not be of any help any mediated game?
So at end, the mediated game is just a game.
Yeah,
It's a game, and it's just a game. And now, if you like to, if you already have, you don't need to know even. So if there's a mediated game, it already has a certain kind of payoffs. And if there is a strong equilibrium in this game, and introduce a new mediator.
So what kind of payoff it has?
Oh, that's Uri's question. Currently, we ignore the incentive of this mediator. So the mediator, we know, will get money basically because of, he helps these agents in a particular way. But the source of money,
My question is very simple. If I have a game, can I check whether it's a mediated game or not?
you don't, for this kind of thing, you don't need to check that. There is a game.
So if there is already a strong equilibrium, then adding a mediator
Will not
doesn't
help, yeah.
And if you have a mediated game, which therefore does have a strong equilibrium, you might know it as a strong equilibrium. You don't know whether it's been
By mediation or
by
not?
mediation or by some other thing. You add a mediator to
It
it,
will not
that
help.
doesn't help.
It doesn't help.
If
So
the
I think
original
you-
mediator was optimal, then there's no need for another.
Yeah, exactly. If
Well,
you
but I
wish.
think you're saying
If
more
you
than
wish.
that. You're saying if that nobody can do more than a single mediator.
Yeah, that's correct.
So you say if the original mediator was optimal, and so he says, well, if, oh, I see. So I guess he's assuming the original mediator will find the optimal
Man
strategy.
maybe was asking, what if the mediator is not optimal? How would you know that?
So again, for us, it's anything that can be implemented as a strong mediated, as a strong equilibrium. You'll not change the set of strong equilibrium. This will be exactly
We
the
assume
same
that all
set.
mediators are like perfect and are Nobel Peace Prize winners.
Yeah, sure. So one thing that I need to do like 5 minutes, because this is almost, I don't know how many people see me, but there is a video. In fact, it refers to something which is almost a bug in a very famous paper. So the idea is as follows. So what does this connect? So this connects to a very seminal, really one of the nicest papers in game theory, and to a notion which is called a C-acceptable strategy. So that's the closest things, and before jumping ahead, I'd like to connect it to this. So things I guess that many of you don't know what is C-acceptable strategy. I'll just say what it is. So the idea is as follows. It will remind you something since we have seen mediators. A correlated strategy, C, is called C-acceptable. By the way, these are not the same C's. It's a bad notation that now that strategy is just C-acceptable. If there exists a vector of correlated strategy, one for each subset, such that the correlated strategy associated with the set of all agents is just C, it's just the right strategy C, and for every subset of the agents and every correlated strategy of them, there exists some agent such that if you, in a sense, deviate to this correlated strategy, I see the faces here, it's not graphs now. So if you deviate to this thing here, then this agent will not gain. So what does it mean? It's just basically saying, look, there is a set of correlated strategies for each subset of the agents. Now, if some of the agents behave differently according to another correlated strategy, then basically the rest of the strategies for the rest of the agents are defined. So in a sense, deviation to another correlated strategy will not be beneficial. It's almost what you heard before that. Yeah.
Sorry, I know I am a little confused.
Yeah, let's go over
In
this.
C acceptable, what kind of object is C? Meaning
C is a correlated. You have a game. A game has a correlated strategy. What is correlated strategy? Is some probability distribution over the strategy profiles, over the things that can happen in this game. C is just a notion. Aumann call it a C acceptable from correlation.
Oh, it's
Let's
not.
call it
Yeah,
Alman
yeah.
acceptable.
Let's call it Aumann. I said in a minute, this C and C will kill you.
It's not a parameter.
Will kill you in a minute. I said it.
Yeah.
So if there exists some vector of strategy, one for each subset of the agents, such that what will be in a sense implemented if all of the agents in a sense, when you talk about this N, it will be exactly this C, and any subset of the agent in a sense use a different correlated strategy, then if you combine it with the strategy prescribed for the rest of the agents, then one of the agents will not gain. again, I don't like, I almost, it looks very similar to what I mentioned before. In fact, if you look at the literature, basically people, what is new in the notion of mediator? In fact, I can say something like the following one. Say, look, you have a C-acceptable strategy. So here's the mediator. The mediator just, what is new in your concept of a mediator? Just tell each agent, if this set of agents come to you, then do that. If another set of agents go to you, then do that. And in fact, this inspired a lot of work. Our basic claim that initiated this work from the foundations is the following proposition. It's like a bug, but I'll not use this terminology from this point on. Every strong mediated equilibrium is C-acceptable. However, as we showed, the converse to the above is not true for very illuminating reasons.
Wait. Why do you say it's a bug? I want to understand why you say it's a bug.
Okay. It's not a bug.
Well, no, it's not a bug.
Everything is defined. You say, basically, people look at this kind of thing, don't define a notion of a mediator. They define a concept, a solution concept, which is called C-acceptable strategies. Basically, they say, look, for this set of agents, I'll use this. For this other set of agents, I'll use that. And deviating from all of this kind of thing is not beneficial. It's defined mathematically, it's well defined, it looks very similar. But there is no notion of a mediator. So what is going on here? So what is going on here is the following thing. I wrote a whole slide for this talk about this. I try to convey it. A C-acceptable strategy used by a mediator is not necessarily immune against what I'll call Trojan horses. So the idea here is that a subset of the agents may correlate in a way that in some realizations, a subgroup is pretending to cooperate by sending the right messages, and this may be beneficial because the Trojan horses will be part of a punishing group and may get a very high payoff for this. So what is the idea? Implicitly, it is assumed in this foundational definition that in a sense you know who are the deviators. But if you talk about correlated deviation, Uri and I can collude in a sense that we flip a coin and say, look, with probability half, you go to the mediator, and probability half, and I'll participate in a particular way, in probability half, we do the other way around. So the mediator cannot really, just can see who comes to it and who didn't come to it. He doesn't know who are the deviators. So one can show that this kind of, what can happen now, the mediator, this kind of thing basically tries to punish the deviators, but in a sense, you may collude in a nice way, such that when someone tries to punish you, in fact, this punishing group gets a lot of money, and basically, so you can build, build nice tricks like that.
So wait a second. So instead of getting punished, you're actually part
of a punishing group. How it comes? Again, I'm just waving my hands here. So the idea is as follows. We collaborate, and we flip a coin, and, basically it turns out that in order to punish a guy, in a sense, I'll have to use some punishment that will benefit, in a sense, the people that come to this mediator. Now, if I do this deviation in a clever way...
So it sounds very non-incentive compatible, somehow. There isn't a notion of incentive compatibility here, but it seems to violate my gut notion of incentive compatible. That there's somehow a way to cheat here.
Yeah. What I'm saying, there are additional ways of cheating.
Right.
That are not when we talk about mediators, when we like to formalize this notion of mediators, that are not captured by the notion of C-acceptable strategies. This basically what we mean.
Also true, in a sense, in the C-acceptable strategies, because there you could say maybe there are several players who are really, in a sense, just one player. Mm-hmm. And then the deviation from the C-acceptable strategy says that one of them would be punished. Mm-hmm. But maybe the others gain.
No. So we got.
And then together they gain.
So we got. Yeah, that's also not really. So we don't. We just talk about the deviation of strong equilibrium in Ullmann style. We talk about other definitions. At least one of them doesn't gain. That's all. That's all. So even in this sense.
Once you make this definition,
yeah.
Once you have collusions, this definition becomes meaningless because one doesn't gain. This one may be part of a coalition, who the other members do gain, and together they're happy.
Yeah, you talk about the situation where you have monetary transfers or something like that. It will not change, by the way, the result. So the idea is it still is different. We need to stick to one particular definition. So we stick to Aumer's definition in order to be consistent with this paper. We can look on other definitions. The definition is that you cannot transfer utilities, and basically if one agent doesn't gain, then it's already not a profitable deviation. One can talk about other definitions. We'll see them if we get there. So the idea here, I can build to you a game.
Andreas has...
What you were describing was using Aumer's definition, right? I mean, Aumer's definition says if a group does something, if a group defects, somebody in that group isn't gaining.
Mm-hmm.
But it doesn't say anything about the people outside the group.
Mm-hmm.
They may gain, and therefore if one of these gaining outsiders is colluding with the defectors,
mm-hmm.
the net effect for the whole colluding group may be a gain.
Mm-hmm. And the moment you formalize the notion of mediator, we need now to specify this mediator, this creature, what he can see, what he can't see. And we'll get into this, but I'm warming you up on this. So basically this is a game. This is a game that creates some noise. Basically, the idea here, I just go very...
What you're saying in a sense is that with the mediator, the difference is that if you did not allow monetary transfer before, in a sense now the monetary transfer is going to...
No, because if there are correlated strategies, still you can do something like money. If you allow correlated strategies, you still allow correlated strategies. You can allow correlated strategies. The difference is that you know who are the deviators, basically, implicitly, when you talk about C-acceptable strategies. You know who are the deviators. But if you're a mediator, you just see, you mix. The trick point concept, mathematically, is that the set of actions include both the original actions and approaching the mediator, and you can mix them. So the idea is basically, in Aumer's kind of concept, what you do is either you give it the right to play, or you can make perhaps strange mixtures on the original actions. But you cannot mix the two of them. This is the main difference. So this is a game that shows you that this kind of thing exists. So it suggests, this was like a long motivation, it suggests that explicit modeling of mediating devices is important for determining reasonable outcome in situations where agents correlate their activities. It means we really need to be serious about these mediators and what they see.
Mediators who were implicit in Aumer's C-acceptable.
Yeah. So basically, they could have seen, and we'll talk about this kind of mediators in a sense, they could have seen your deviation. So assume that Jennifer and Uri like to deviate. They have a I am the mediator. You go and say, look, Moshe has some conditional contract, crazy conditional contract. So basically, if you are the deviator, the only deviation that you can do is to go to another room and decide on some correlated your activities in order to transfer money or whatever, and come to me. But and participate in the game directly. But I know you didn't come. I can do various kind of things. What happens when there is a mediator? You say, you go with Uri to the other room and say, Uri, you know what? Let's flip a coin. And with some probability, you'll go to Moshe and say, okay, I'd like to participate. And I'll go and submit some action A. I'm mixing the mediation, approaching the mediator with the action. So that's the flavor of it. So after saying and selling you that we need to sell mediators, so the question is, how much mediators can help? So we'll talk now about very simple mediators. These mediators basically cannot see anything. They are uninformed mediators. Later, inspired by discussion for people distributed computing, we'll talk about routers, which are more informed mediators. But now we talk about uninformed mediators. I just can all that I have is my reliability, and I can offer this conditional contract, and that's it. I cannot enforce you to participate in a particular way. So here is a result, which is, by the way, not hard, that says that, it's not just the prisoner's dilemma. Every two-person game has a strong mediated equilibrium. This is, if we like to talk about two-person, then always there is a two-person game. Now, I'd like to state to you a general theorem, and knowing at least part of this audience after 10 days, I know that there is missing terminology in this slide. We'll read it together in case that game theorists came, and then we'll talk about two corollaries of this that I can easily explain. And I'd be happy to talk with you about the general theory. So just like put it together. This is like a characterization of the power of mediator. So let gamma be any symmetric game. So what we talk is, from a game, we can build what is called a transferable utility game. So this is a game in coalition form. Basically, it's like a game where a coalition plays against the other agents. And the theorem says that if what is called the core of this TU game is not empty, there exists a strong mediated equilibrium with optimal surplus, where each agent gets an equal share, and this condition is also necessary. So that's just to relieve that I state the theorem. So let me show you one application of this theorem, and then a corollary of this that you'll be able to take home if you lost me. So, so here is a nice application. We'll talk about more applications later. This is a nice model that I like, which is called congestion game with failures. So what is congestion game with failures? Everything is written here. But basically, we have a bunch of resources, and a bunch of agents can select among these resources. There is a certain delay associated with each resource, which is just monotonically increasing. The more agents come, the more delay there is. Now there is now what you care about is delay. So you may like to use several of the resources, and in order that your package will be delivered as soon as possible. But you pay for each delivery. You pay a cost for any resource that you submit. So formally, what you get here is that the expected payoff of an agent is the worth of the task for him times the probability of successful completion of the task by at least one of the resources, minus the minimal delay executing the task, and minus the cost of submission. You see, that's quite general kind of setting. Those of you that know about congestion games and the zillions of studies, this is just an extension. It says, look, you have many resources. You can select among these resources. You care about your delay. And you pay for each resource that you select. Each resource may fail. So you may decide to choose many of the resources. So the case of probability 1 is well studied. And so it turns out, it's well known that basically strong equilibrium of any type cannot be guaranteed for this class of games. However, the previous theorem will imply that the strong mediated equilibrium exists in any game of this type. So although we'll talk about routers in a minute, so just think about a situation where this is really a congestion setting, but you have a router that cannot enforce you to anything. You say, if you come to me, I'll send your message here. If these guys come to me, I'll send you message there. And suddenly, because there is such a reliable entity, you get that you can really get very nice kind of output which is stable against even correlated deviations. So here is what I said, an abstract theorem that you can take home. And this is called the notion of K-strong equilibrium. What is K-strong equilibrium? It talks about deviations until and against coalitions of size at most K. So what is Nash equilibrium? One strong equilibrium. Yeah? Nash equilibrium that we all heard about is being stable against deviations of coalition of at most size 1. If you'd like suddenly to be stable against coalition of size 2, game theory mostly gives you negative result. In fact, I don't really know about a natural class of games where we talk about correlated deviations of the agents of size 2, then you are able to get a nice result. So let's use the idea of mediators. And here is a result that it's easy to state. So let gamma be any symmetric game in strategic form.
Excuse me, sorry. By symmetric, you mean that you permute the players
and the payoff. Yeah.
Okay, and strategic form means?
Strategic form is just game matrix. So it's just a general game. Sorry. So we'll talk about non-symmetric game in a minute. So let gamma be any symmetric game in strategic form. So the games that you have seen in game theory, and if we take a class or heard a talk, any kind of such game, a finite game, So basically, and what you say now is you'd like to be stable against deviations. So what we are able to show is let k be some integer between 1 and n. So if k factorial divides n, then there exists a k-strong mediated equilibrium leading to optimal surplus. And if k factorial does not divide n, then there exists a symmetric game with no k-strong mediated equilibrium.
But there's an almost equilibrium. People can't do a whole lot in that case, right? I mean, there exists a game in which the amount that the deviators can gain is pretty small.
It may be small,
Yeah.
but what results tell you in a positive sense, you say, look, you have a symmetric game, any symmetric game. And you always know that there is a Nash equilibrium. If you have a mediator, if this game have an even number of players, why does it matter? Even number of players, 16 and not 17, then we can guarantee that you'll be able to have a two-strong equilibrium. I can have a mediator that will implement the optimal outcome. The optimum is well-defined in symmetric games. That will be stable against deviations by pairs. As an anecdote, because we looked at more realistic example, if you talk about the Israeli parliament and there are 120 members there, then you'll be stable against deviations of size 5. So you'll be able to be stable against that. I can show you very nice war stories.
Are you going to give us any intuition as to why the...
In fact, no. I can do it. The idea will be... let's leave it. It's.
I mean, could you show us n equals 3 and k equals 2? I mean,
So for example, I'll tell you why the case of 2 it's easy. Why we have two agents. Why in the case of two agents it will be easy to show for two-person games. You always have a.
No, but I want to see the other.
He wants to see the other.
So the idea here, yeah. So we'll do it as for the basic. Okay, I say something, although it's not a
But
proof.
this is assuming, of course, if you had a mediator which did not treat everybody in the same way, then they wouldn't be indistinguishable, then you wouldn't get a k factorial there. I mean, you could have a mediator. There are occasionally mediators who favor one side over another, or he'll do different, and so if you did that, then you wouldn't get I assume the k factorial is coming from the fact that the parties...
So I'll give you a hint. I'll give you a hint.
indistinguishable
I'd like to
from
walk through something, but I'll give you a hint. The idea is as follows. Let's think about the optimal algorithm. The optimal algorithm will be what? Make some symmetric game, do some permutation of the agents, and let them, use the optimal strategy profile if everyone plays a different role at each time. So assume now that there is a deviation by a pair of agents. Again, it's not a proof. So what is a deviation? It means that this pair of agents basically can manipulate in a way that if they'll not come to the mediator, even the mediator will fight against them, they can get more than 2 over n of the optimal surplus, which is what they get usually. But if every pair can do it, then let's every pair do that, and basically we'll be able to get more than the optimal surplus. Are you with me? That's of course not a proof, because there are many things that this can do, but in a sense this will be like a contradiction to the fact that you cannot obtain more than 1 over n of the optimal surplus. This will be like a counting argument. Of course, it's much more. It's not a proof. And why it will hold? Why we'll need this? We cannot do that if 2 will not divide n. And now, if you talk about deviations of size k, it turns out in order to do that, we need that 2 will divide, 3 will divide, 4 will divide, and so on. Again, there are many tricky points here. So, okay, we'll jump over this. This is connection to program equilibrium, because I'd like, in the limited time that I have 2 options. And yeah, I'd like to mention to you one thing. How much time do I have, by the way?
Let's see. We started pretty late, so maybe another 25 minutes.
Okay, so there are 2 things that I'd like to tell you about. And I don't know what will make you more excited. So try to wake you up. So one thing is extending this work to more complicated type of mediator. Again, the agenda is you have a mediator which we believe exists in any system. And the idea now is try to find what is the power of mediators that will allow some positive results. Our mediator weren't that complicated until now. So that's one thing that we can do. And I'll show you one thing. Another thing is to extend this theory to games with incomplete information. In games with incomplete information, I wanted to tell you about particular application, in addition to the theory, which is to add auctions. So I'll spend like 10 minutes on each. And I'll dig in that much insight. So we had this simple form of mediators. They were very, very limited. Why they were very limited? Because basically we assumed that this mediator knows nothing about the actions of the other agents. So let's take seriously the example that we talked about on seeing other agents' actions. So my very good friends in distributed computing tells me about, this is a router that has been, routers as designed. Basically, if you have a router, a communication network, then messages pass through it. In a sense, you can see the actions. You cannot really, in many cases, control these actions. But independently of this, you can offer a conditional contract that says, look, if you like it, I'll perform actions on your behalf. If you'll send me this and that messages, I'll do this on that behalf. So these are two like orthogonal capabilities. And basically, you may be able in this situation to condition on the actions also of other agents. Now, of course, this may be too extreme. This may be too extreme. You may not be able to see all actions. You, as perhaps like in Oman kind of thing, you may be able not to see the actions, but the programs of others. So there is a whole hierarchy of mediators that we study. And this is long for this short talk. And how do I do that? OK, so the idea is as follows. We distinguish between two types of information available. Information about the realizations of the other agent's actions, whether you can see the actions, and information about the other agent's programs. And basically, we create a whole lattice of mediators. So what is written here is the mediator that we discussed before. Omega basic says this is a mediator that cannot see the other agent's actions and cannot see the other agent's programs. Omega full is something that can see the agent's actions and the other agent's programs. Omega basic C full is something like Aumann case, where basically you can see the agent's programs, but you cannot see the realizations. And this is the router example, which we really like, which we see the realization but cannot see the program. And we make a whole characterization of what is more powerful than another in implementing desired behavior. What is nice to know is this doesn't collapse, that there can be a situation where seeing the programs is more useful than seeing the realization, and the other way around. This is what is important to know. So I saved to myself many, many slides. And I'd like to tell you now about another very positive results to take home. So now we are going to be really crazy from the game theory perspective. We'd like to ask something very, very demanding. In a correlated, super strong equilibrium, correlated deviations by any subset of the agents cannot benefit one of them without hurting another. So this is a situation where we like to be stable against deviations, such that a useful deviation will be that, look, we correlated our behavior. Correlation is like monetary transfers, basically. And basically, look, one of us gained, and the others didn't lose. So we'd like also, it's not that everyone should gain, like in Aumann. It's also not the case that they cannot correlate their behavior. They can do both. This is a very demanding concept. Now we talk about a very general class of game, which is called a minimally fair game. What is a minimally fair game? It has only one requirement. In a minimally fair game is a game in which all actions are available to all agents, and all agents who select identical actions get identical payoffs. That's all. It's not just symmetric games. Symmetric games are of course, minimally fair, but here it's job scheduling games, to those that knew about this, fit into this as well. It just means that if Uri and I select the same resource, or do the same act, we'll get the same payoff. So if you are in a competition and we enter a boat competition, if you enter the same boat, we'll get the same kind of payoff. Of course, it may be that it's important whether I'm Uri with the boat or with Jennifer in the boat. It may be very important. It's not something symmetric. But if we choose the same thing, we'll get the same payoff. So job scheduling is there and many, many, many games there. What we like to implement is something which is very popular both in the game theory community and the computer science community. It's fair efficient outcome, or min-max fairness. An outcome in which the payoff of the player who gets the minimal payoff is maximized. So in the symmetric game, you just need to get the optimal payoff. But what is the best in the case where the game is not symmetric? So we look at the worst agent payoff, and we like it to be maximized. If there are tools like that, we do it in lexicographic ordering. So this it's like a canonical requirement in communication networks in other disciplines. And here is our main theory. Let gamma be any minimally fair game. Then a fair efficient outcome of gamma can be implemented as a super strong mediated equilibrium relatively. What is this? I remind you, this is the router example that we had before. So if you have a mediator with capabilities as the router that we mentioned before, that can have its own reliability, can offer conditional contract and see messages, then suddenly all of the minimally fair game, you can implement them with something very, very strong. So again, what are the ramifications of that? Sorry for being excited, I don't know. So the idea is as follows. Look, in many situations, we have mediators. In any system almost that I know, we have mediators. So the mediators which are informed, like uninformed, exist in most any system. In your system, you have something like a router. And you prove to me, and there are zillions of papers talking about that, get this stability and the other stability. This router can be used in order to implement desired behaviors in any such kind of situations that will be stable. It will be optimal, and it will be stable against very, very sophisticated kind of deviations. Those of you that don't like to do, I just prepared like 2 other theorems to people that don't like to see people that can see everything. So assume that we can observe only, that's just an example of theorems, only the action of the highest agent in some predefined arbitrary ordering among the ones who didn't choose the mediator services, just some information, some bit about the information of on the behaviors of other agents, then there are these 2 theorems. Given the above condition, the relaxed information structure, a symmetric optimal payoff of gamma can be implemented as super strong mediated equilibrium for any symmetric game gamma. So the same kind of results for symmetric games in the relaxed information structure, and also, given the above condition, we can obtain fair efficient outcome in as a strong mediated equilibrium, any minimally fair game. What is written in this theorem is something that I could have cheated you before that. It says the following thing. Look, for any minimally fair games, to the job scheduling games, to all of these kind of games, you can obtain stability against correlated deviations, not in the super strong sense. So what we dropped here is that in the relaxed information variable, you don't gain strong deviations. It's not the super strong, it's just the correlated deviations. Again, something that you typically don't have, but it's not in the super strong sense, but just in the standard correlated sense. So there are applications that we can spend time on. In congestion games, there are many applications. Basically, we have a full characterization about the type of mediators that are needed in order to handle various kinds of congestion games. This completes previous work by Ola Rozenfeld and myself that talk about when do you have strong equilibrium in congestion game, and extend work by Loyon and Ron Holtzman that also dealt with this. There is a nice graph theoretic representation that says in which graphs you have strong equilibrium and which graph you have strong correlated equilibrium. This is a talk for itself. So we have a paper that filled this up completely, and now basically as application of this work, we can fill it up for different types of mediators. If you have mediators that can see that, whether you'll have this or you have that. So finally, take 10 more minutes of your time. So I even not give the conclusion so far. Yeah.
This subject. So you say these mediators exist, and now they offer a contract to the other.
Just conditional contract, yeah.
Player. So how complicated is this contract?
That's a good question.
To read the contract.
Yeah, the right question, Rory. Yeah, we of course look at it. So in general, in this talk, we didn't talk about complexity at all. Of course, there are an interesting question about what is the complexity of this, what is the complexity of finding it. You know, we have some, you know, there is a whole orthogonal.
The general theorem offers an exponential size contract?
Yeah, in this, we didn't care about that.
You have to leave room for the lawyers.
No. By the way, this is a question that comes also from economists, and you know, of course, they don't think about complexity theory. You just say, okay, fine, I have 100 agents. So what is the contract that you offer me? Just write it down. Let's see you. So we look at the complexity of this. I'll be able to share with you. I don't think in this talk we didn't touch at all.
But it's big.
But
it's big.
If the complexity is big, it depends. It also depends on the structure of the game that you have.
But
we talk
you
about.
can come up with games
Let's put it that way. I can answer you if you like as complexity theory. So if you look at explicit representation, it can be log SNP. Okay, it's log SNP complete. Okay, that's in general. Now, if you don't care about log SNP, so we can talk about there are situations which would be polynomial, and of course, what we care mostly is about succinct representation. Giving a graphical game, if you talk with me, it will be local effect game. Other kind of succinct representations, what we can say about complexity. It's we can spend hours on that. It's a whole, the whole direction. I'll just start to sell to you the basic, the basic stuff. So basically just conclusions so far, and then just because that I'll not say many conclusions, what is important to me is this theory of mediators who can hack on behalf of and only of agents to give them the right of play. We showed that this is a general setting and how it extends difference from classical work in game theory. And what is perhaps more important, provided evidence for the power of action mediator in obtaining multi-agent behavior, which is robust against deviations by coalitions. I'd like to spend like 10 minutes, if you allow me, about the incomplete information setting, because I think it calls for many, many applications. So what is the incomplete information setting? Until now, we have discussed mediators in games with complete information. In a complementary work, we define and analyze mediators in mediated equilibrium for games with incomplete information. The application that I've chosen to present to you very briefly will be for two-position auctions. By the way, this work that was presented, the last one was presented like 3 months ago, already has several extensions by others that I'll be able, to show it. Very, very nice. The other work. So let's skip here. So again, without entering into too many discussions about game theory, so what are games with incomplete information? I'm doing things amazing, presented in this talk. Basically, what we have here is you may be playing many games. The right thing to say about games with incomplete information is that you may be facing many games. What is an auction? There is possibilities to many games. If you tell me how much the product worth for each one of you, that's a game with complete information. But I don't know how much the product worth for each one of you, so there are many games that may be played. So these are called states of nature. And basically, each agent gets what is called a type. A type is just a signal that says, look, I'm the raw agent. I learn that the game is one of these two. So in an auction, for example, what will be the type of the agent? For example, his valuation of the object. So it says it's not all of the games possible. It's just the games that the value for me is $5. Again, I'm going fast. So the classical work in game theory assumes a probability distribution on these games. So the idea now there is a concept that is called the Bayes-Nash equilibrium. So there are two Nobel Prizes, but in fact it's one concept that says that there is a Nash equilibrium where you take all of these probabilistic assumptions. So there are solution concepts to games where you have probabilistic assumptions. There is an equilibrium. Like if there is a probability distribution on these games, there is a notion of equilibrium that I can communicate to you, the Dov does not know, in several minutes and show existence under certain conditions. The only thing here, what happens if we don't know this probability distribution? It's not common knowledge. So what will be a good solution? So in the auctions that you find, for example, in Google, Yahoo, perhaps in Microsoft too, You know, people tell you a lot of stories, but if this is a game with incomplete information, you don't really know what is the equilibrium there. People do analysis to the games with complete information. Very nice. But if the game with incomplete information, you know, we don't know. And there is a solution concept, which is called the ex post equilibrium. What is the ex post equilibrium? It basically tells you, look, a miracle happens. I can tell strategies to each of these agents such that it not be beneficial to the agent to deviate from its strategy, assuming that the other agents stick to its strategy. This is not a dominant strategy. Stick to its strategy, but no matter what is the information or the type of the other agent. So if I'm using this strategy, then if this other agent stick to that strategy, by deviating here, I just lose. By deviating here, I just lose. If you use if this type of others and use this strategy, then if I deviate, I just lose. And if I deviate, I just lose. And this happens simultaneously to all agents. That's a wonderful solution concept. It's ex post equilibrium. It's very nice solution concept. Its only problem, it almost never exists. So now I'd like to repeat the same story that I told you about strong equilibrium to tell you about ex post equilibrium. I'm a mediator. And now I'd like to implement some desired behavior, let's say, in this ad auction. And what I'd like to do is to implement some efficient outcome, some nice outcome, in this auction as an ex post equilibrium. So what I should do now, I have a conditional contract, but you have information. So I need to approach you guys and say, look, guys, come give me your information. Give me the right of play and give you your information. I need to design now the contract in a way such that now in the mediated game, what will happen? It will be an ex post equilibrium to give me the true information, to go to me, to give me the true information, and as a result, the outcome, the right outcome, will be implemented. Are you with me? Is it fine? So this is the theory that we built. In the last 5 minutes or so, I'd like to show you how it applies to position auctions. We have general results, but I'd like how to apply. So in fact, there are two types of this. This is I can play the bad guy or the good guy. The bad guy means let's call it by its name. The mediator is a bidding club. It tried to help you guys doing things. By the way, this is the way that we started already 2 years ago, talking about this. But now let's be the good guys. Say, look, in an auction, there is a very nice output, efficient outcome. Basically, there is only one type of auction that can implement to you efficient outcome as an ex post equilibrium. It's called the VCG auction, if you heard about it. So this is a very nice auction, which is not implemented now by any of the leaders. So basically, it says the following, this auction, and those of you that don't know, basically it says something as follows. It says, look, give me your type, your secret. I'll compute an optimal allocation. And each one will pay a tax which is proportional to the amount of harm we cause the other agents. So we can define it formally, but this auction is wonderful. It implements the efficient outcome. It's truthful. It's truthful to say the truth. It's truthful to revealing the types is the right thing to do. So the question is, can I build a mediator that will implement to you the VCG outcome? People design crazy auctions. So here I'll jump here on the theory. So VCG is a particular one. People started with self-price position auction, which says there are these ads. I guess the people know this setting or not. In Microsoft, people need not. So basically, there are the ads on the right side of Google. Basically, you submit a bid, and people get this kind of slots based on their bid. Technically, it's not just because of the order of the bid. There is something which is called the quality effect, which multiplies this. All of our results will follow through that. So basically, you order these bids, and basically each agent in the self-price auction pays his own bid, in the next price position auction that I hate that name that people give it the GSP. I really hate it. It's simply incorrect. In the next price position auction, what an agent will pay is the next bid, the bid below it. And there are many other auctions that people invented, by the way. So the key point is there is no ex post equilibrium in the self-price and next price position auctions. So we ask the following question. We are the experts in mediators. So in which position auctions can the VCG outcome be implemented? If possible, then we can use it for coordinating EDR's behavior, obtaining useful output using simple truthful bidding. So I can just come and say, look, I'll give you a mechanism, and you know what? It's worthwhile to you to participate in this mechanism, and you know what? It's better to you to reveal your truth, and I'll use the original auction. I'll just coordinate your behavior in the original auction, and what will be implemented as ex post equilibrium is exactly the VCG outcome. Can it be done? So it turned out that there are auctions that it can be done, and there are auctions that it cannot be done. And again, I jump here because I prepared something too long. I apologize. So this is the theorem. It's an if and only if theorem, basically, that says the following. Let G be a position auction. If the following conditions hold, then there exists a valid mediator that implements the VCG outcome in the G. What does it mean again? It means that I can build a mediator that everyone will approach, reveal their valuation, it will participate in the auction, and all of this will be an ex post equilibrium, and the desired VCG outcome will be implemented. So the conditions are as follows. Position payment depends only on lower position bids. So for example, if you talk about self-price auction, this will not hold. Self-price auction will not be able to do that. The other condition is trivial, which is called VCG cover. Any VCG outcome can be obtained by some bid profile. What does it mean? If there is some outcome that no matter what I'll send to this auction, it will never output these payments, I cannot do anything about that. And the third condition is this is like the serious one. This is, we need to be careful. It's also not that trivial because it's not easy to establish, but basically we need to require that G is monotone, which means that if the bids are increasing, then the payments in each position are not decreasing, because there are nice auctions which this can happen. And it turns out that each of these conditions is necessary. So this is the result that we have here. So some corollaries. The important corollary is, to those of you that know the practice, there are many corollaries, is the quality effect, that valid mediator exists for existing. I don't know if to write Microsoft here, you will tell me. Position auctions, where the quality effect of agent is, the agent has what is called a quality effect, which means you don't just rank agents by their bids, but you multiply it by something which is proportional to how good this ad is. We can define it formally, but
I mean, like the click-through rate.
yeah. So yeah, in fact, the quality. I use the term quality effect as used by Google. Others call it differently. So basically, but we talk about the same.
Google also has what many people call a fudge factor. That's not what you're talking about.
No.
You're just talking about something like the click-through rate.
Exactly. Okay, so let's skip this. I'll put some conclusions on that. So the conclusions on the first, this part, this was very, very brief. We introduced the study of mediators against with incomplete information and applied mediators to the context of position auctions and characterized the position auctions in which the VCG outcome function can be implemented. Some references, in fact, the only references that exist for all of these types work on mediators. In complete information, there are almost none. We need to go to 59, to Aumann. We have the whole credit for these guys. In games with incomplete information, there is work in the context of collusion. The real interesting related work is this one by McAfee and Macmillan. And McAfee now joined forces with your competitor. And this one, which is technically more complicated, which is going to work with Bat, Little Brown, and Yoav Shoham, they talk about collusion when in cases there are many mediators. So let me just put one more slide, since I'm a visitor here. So I'll say the following. Look, what I did could convey to you, but I don't know if it wasn't not too dense for that, is this point. So we have a whole agenda, to those of you that didn't notice, that try to get some positive results in the context of game theoretic reasoning. So a pitch of 2 minutes for this audience, that I do for every audience. So I work for many, many years in this connection between game theory and computer science, and basically the main problems are open. What are the problems that are open? If I have an agent, the question is how this agent should behave in a given game, completely unclear. If we have a situation where we have an entity that needs to give the agent advice about how they should behave in a given game in order to be followed by rational agents, we are more or less stuck in the Nash equilibrium. So we try to do something in this, and this is a very ambitious research agenda that started like 7 years ago, after many years of working on this subject. And what we describe to you here is this point here. And this point here let's take seriously the idea of mediators. One word about programs, Adam is not here, but it turns out that the notion of mediators connects very nicely to the notion of program equilibrium. What is the idea of program equilibrium? It's very important to computer scientists to know. Typically, when people talk about computer programs, they're not different between computer programs and agents or players. So in fact, we talk with game theorists to say, so what is this, all of this computer science? I don't know. So let's call it player, let's call it agent. It's the same thing. So it turns out in an observation that we had several years ago, that if you take seriously the notion of computer program that can do things as defined in von Neumann work, they can do wonderful things. In particular, if you play with computer programs as defined in von Neumann work, we can get something like cooperation in the prisoner's dilemma. So in one-shot game. And it turns out that this notion of mediator is highly related to the notion of program. So basically, anything that you can obtain with a mediator, which is a standard entity, you can obtain if you allow the agents to use computer programs as defined in von Neumann.
So is that what Adam and his father did?
So the problem is called program. The quick history in Adam is not here, so he should tell the history. But the story is that there was a paper called Program Equilibrium that I published, like 4 years ago. And immediately after that, Ehud called me home, say, look, that's a very nice concept. We are starting to work on this. I said, oh, we are starting to work too. And we realized that we're doing things in parallel, and there are papers like 4 authors now. That's, interesting stuff. So the idea is basically to try, again, not like to talk about too much in general. So the idea of mediators, again, what I like to convey here, I'll stop. In many situations, you need to think, economists don't think that way. Again, this is my best friends. They think about, no mediator. Who is this mediator? In fact, who is started to say, who pays this guy? He's a player. Forget it for a minute. We'll do it later. We have a mediator. We design system. But we cannot really tell all of the agents how to behave. It's not the case that either we tell all of the agents how to behave, or they just behave as their own. Very popular these days to compare this in computer science. But this is not the only way. This is not two extremes. Typically, you have games exist. You don't design new games, and you cannot enforce behavior, but you have administrators, or brokers, or clubs. So what we formalize are these notions, and we see what are these notions that are needed in order to obtain the desired behavior. And I'm waving my hands enough, so I'll stop here. Okay. Thank you.